Tonight, we are going to explore the most powerful space telescope humanity has ever built. Quietly turned its golden mirrors toward the nearest sun-like star in the sky. It stared for hours, and it found something that shouldn't have been there. A faint point of warmth, glowing in the infrared, positioned at roughly 2 astronomical units from Alpha Centauri A. A signal that statistical analysis said had less than a 1 in 10 million chance of being random noise. A signal that passed every test the team could devise to expose it as false. A signal that, by every metric scientists use to evaluate evidence, looked like a planet. Then it vanished. Follow-up observations found nothing. The region where the object had been detected showed only empty space. The planet, if that's what it was gone. And this is where the story gets genuinely strange. Because the scientific explanation for the disappearance is not that the object was never there. The scientific explanation, supported by computer simulations of millions of possible orbital configurations, is that a real planet following certain perfectly normal orbits around Alpha Centauri A would disappear from the telescope's field of detection at almost exactly the times when the detection failed. The planet might have vanished not because it doesn't exist, but because it moved into a part of its orbit where current technology simply cannot see it. That is not a comforting explanation. It means the question of whether our nearest stellar neighbor hosts a world is still open. It means the most powerful telescope humans have ever built looked at the closest sun-like star to Earth and came back with an answer that is half yes and half we don't know. Tonight, we're going to understand why. All of it. The physics of why this target was considered impossible. The engineering of how a team made the observation anyway. What the data actually showed. Why the disappearance is not as simple as a failed detection. And then we're going to go somewhere the other discussions of this story haven't gone. Into the parts of the physics that haven't been clearly explained. The things about this system and this detection that are quietly more unsettling than the headline. Because the story of the James Webb Space Telescope and Alpha Centauri is not just a story about whether one planet exists. It's a story about how close we are to finding out whether the nearest place in the universe that could possibly support life actually does. Before we begin tonight, take a moment to like this video and subscribe to the channel if you haven't already, and tell us in the comments where you're tuning in from. We read every location. It means something to know where these conversations are reaching. Now, let's go. Alpha Centauri is not a star. It is 3 stars. Most people know this at some level, but the detail of it matters for understanding everything that comes next. So let's sit with the full picture for a moment. The system's 2 main members, Alpha Centauri A and Alpha Centauri B, are sun-like stars orbiting their shared center of mass in an elliptical loop that takes approximately 80 years to complete. At closest approach, called periastron, they come within about 11 astronomical units of each other. 1 astronomical unit is the distance from Earth to the Sun, roughly 93 million miles. 11 astronomical units is roughly the distance between our Sun and Saturn. At farthest separation, called apastron, they drift apart to approximately 36 astronomical units, about the distance of Neptune from our Sun. As of the mid-2020s, the 2 stars were at intermediate separation and gradually moving apart. Alpha Centauri A is slightly larger and brighter than our Sun. Its mass exceeds the Sun's by about 10%. Its radius is about 20% larger. Its surface temperature of approximately 5,790 Kelvin sits within a couple hundred degrees of the Sun's 5,772 Kelvin. Its luminosity exceeds the Sun's by roughly 50%, meaning any planet orbiting at the same distance from Alpha Centauri A as Earth orbits the Sun would receive more energy, pushing that planet's effective temperature higher. Alpha Centauri B is smaller, cooler, dimmer. It sits at about 85% of the Sun's mass, with a surface temperature around 5,260 Kelvin, giving it a slightly more orange tint. Its luminosity is about half the Sun's. Both stars are approximately 5 billion years old, comparable to the Sun's age, which means they represent mature, settled stellar systems, not the hot and violent young stars that astronomers most easily image planets around. Then there is Proxima Centauri. This is the closest of the three to Earth, marginally, by a mere 0.14 light-years. Proxima is a red dwarf, tiny, dim, violent. It emits less than 1% of the Sun's luminosity, but compensates with periodic violent stellar flares that blast its orbiting planets with radiation. Proxima has at least 2 confirmed planets and possibly a third. One of them, Proxima B, lies in the star's habitable zone, the orbital region where liquid water could theoretically persist on a rocky surface. Proxima B has attracted enormous attention because of the word habitable zone. But the honest scientific assessment is that a planet orbiting a red dwarf like Proxima Centauri faces conditions fundamentally different from Earth. Red dwarf flares are not gentle events. They strip away planetary atmospheres over geological timescales. They bombard orbiting planets with ultraviolet and X-ray radiation at intensities that Earth's biosphere would not survive. The planet is almost certainly tidally locked, meaning one face permanently roasts under its star, while the other freezes in permanent darkness. The habitable zone of a red dwarf is so close to the star that a planet within it is pulled into tidal synchrony within the first few 100 million years. This is why Alpha Centauri A and B matter so much more. Scientifically, these are stars where the word sun-like actually means something. Their spectra resemble the Sun's. Their luminosities support habitable zones at distances similar to Earth's orbit. Their ages mean they've had billions of years in which stable conditions could have persisted. If you're asking whether there are planets around Alpha Centauri that resemble Earth in any meaningful way, the answer lives around A and B, not around Proxima. And for decades, we had no idea whether A or B had planets at all. The reason Alpha Centauri has been so resistant to planetary investigation is one of those situations where the intuitive logic runs exactly backwards from the reality. Your instinct says, this system is the closest. The closest target should be the easiest to study. The proximity should provide advantages no other target can match. The physics says, proximity is a curse. Here is why. The brightness of a star scales with the inverse square of its distance. Double the distance, the star appears 4 times fainter. Cut the distance in half, the star appears 4 times brighter. Alpha Centauri A sits at 4.37 light-years, which compared to typical exoplanet host stars located hundreds or thousands of light-years away is staggeringly close. At that proximity, Alpha Centauri A appears as the 3rd brightest star in the entire night sky, behind only Sirius and Canopus. On a clear, dark night in the southern hemisphere, it blazes. This is not a star you need a telescope to find. Ancient navigators used it. Now remember what direct planetary imaging requires. You need to detect light from a planet sitting next to that star. The brightness ratio between a Sun-like star and a Saturn-class planet at roughly 2 astronomical units is in the neighborhood of 10,000 to 1. The planet's signal is 10,000 times fainter than the star it's sitting beside. The star is already one of the 3 brightest objects in the night sky. Any instrument sensitive enough to detect a signal 10,000 times fainter than Alpha Centauri A's light is an instrument being asked to survive, being pointed at something of absolutely overwhelming brightness while simultaneously detecting a whisper against that roar. The sensitive detectors that can hear the whisper are exactly the detectors most at risk of damage or saturation from the roar. This is the paradox of proximity. It amplifies the signal of a planet that might exist, but it amplifies the competing stellar background by exactly the same factor. The planet-to-star brightness ratio doesn't improve with proximity. The absolute brightness of both star and planet increases together. Being close doesn't help you separate the two. It just makes both louder, and the star was already catastrophically loud. There is then the motion problem. Alpha Centauri A moves across the sky faster than almost any other naked-eye star. Its proper motion, the angular rate at which it shifts against the background of more distant stars, is approximately 3.7 arcseconds per year. That sounds small. Over a human lifetime, it amounts to a few arc-minutes, less than 1/10 of the Moon's apparent diameter. But coronagraphic observations require a stability measured not in arcseconds, but in milliarcseconds. The star must be held to within tens of milliarcseconds of the coronagraph mask center for the suppression to work properly. Any drift larger than that allows stellar light to leak around the mask and obliterate the planetary signal. Alpha Centauri's fast motion means every observation requires continuously updated tracking calculations and higher pointing precision than any other target of comparable brightness. The binary companion compounds everything. Alpha Centauri B orbits close enough to its companion that both stars share JWST's field of view during observations of either one. No coronagraph can block 2 stars simultaneously when they are at different positions on the detector. Block Alpha Centauri A perfectly, and Alpha Centauri B spills its light across the entire field, creating scattered halos, diffraction spikes, and brightness gradients that can easily overwhelm a planet's signal, or create false signals that look like planets. The galactic background adds a 4th layer of difficulty. Alpha Centauri lies in the direction of the Milky Way's disk, where background stars crowd the field of view. Any faint detection must be ruled out as a background coincidence, a distant star or galaxy that happens to appear at the right position and brightness to mimic a nearby planet. 4 separate problems, each severe enough on its own to make the observation challenging. Together, they created a target that astronomers categorized not as difficult, but as effectively off-limits. Before James Webb entered the picture, every major technique for finding exoplanets was applied to Alpha Centauri and came back empty-handed from A and B specifically, though for different reasons in each case. The radial velocity method measures the Doppler shift in a star's light, caused by the gravitational tug of an orbiting planet. As a planet orbits, it pulls the star in a small circle. The star moves toward us and away from us periodically, and this motion compresses and stretches its light waves, shifting its spectral lines. By measuring these shifts with extreme precision, you can detect the planet's presence without seeing it directly. This method has found thousands of planets. The problem at Alpha Centauri is the binary. Alpha Centauri A and B are themselves moving relative to each other, in their 80-year mutual orbit. This large orbital motion produces a Doppler signal, orders of magnitude larger than the signal from any planet. Separating a planet's tiny signal from the star's large orbital motion requires extremely careful modeling of the binary orbit itself. Small errors in the binary orbit model contaminate the residual and create false planetary signals. In 2012, a team announced the detection of an Earth-mass planet around Alpha Centauri b, using radial velocity data. This announcement generated enormous excitement. In 2016, a reanalysis of the data concluded that the signal was an artifact of the data analysis procedure, not a real planet. The detection disappeared when the analysis was corrected. This is not a story of bad science, but of science working correctly. The subsequent reanalysis was the process doing what it's supposed to. But it illustrated exactly how difficult the radial velocity method is at this particular target. The transit method watches for the periodic dimming of a star as a planet crosses its face. This method has found the largest number of exoplanets in history, thousands of them, through the Kepler and TESS missions. But it requires that the planet's orbital plane is aligned nearly edge-on from our perspective. The probability of any given planetary orbit being so aligned is small, typically a few percent. Monitoring campaigns for transiting planets around Alpha Centauri A have been conducted and produced no detections. This is consistent with planets being present, but simply not aligned to transit as seen from Earth. It does not rule out planets. Ground-based direct imaging was attempted before James Webb. In 2019, astronomers using the Very Large Telescope in Chile and an instrument called NACO, designed for high-contrast mid-infrared imaging, found a faint signal near Alpha Centauri, A designated C1. The detection appeared marginally in processed images at approximately 1.1 astronomical units from the star. But NACO operates through Earth's atmosphere, which constantly blurs and distorts incoming light. Adaptive optics systems partially correct this blurring by measuring the distortion in real time and adjusting a deformable mirror to compensate. They are impressive systems, but they cannot eliminate atmospheric effects completely. The residual atmospheric contamination in the 2019 data was enough that the C1 signal could not be distinguished from a sophisticated atmospheric artifact. It was noted as an interesting hint requiring better data and largely set aside. This 2019 detection became quietly important later, in a way the original observers didn't anticipate. We'll return to it. To understand why James Webb changed what was possible at Alpha Centauri, you have to understand what the telescope was actually built for. Because pointing it at the third brightest star in the sky was not part of the plan. James Webb was designed to see the oldest light in the universe. It was built to study the first galaxies that formed after the Big Bang, collections of stars so distant and so redshifted by billions of years of cosmic expansion that they glow only in the infrared, invisible to any optical telescope. It was built to study the chemistry of exoplanet atmospheres around distant stars, analyzing the spectral signatures of starlight filtered through planetary air to identify molecules. It was built for faintness. Its instruments were calibrated for targets that emit a tiny trickle of ancient photons across billions of light-years of space. Pointing this machine at Alpha Centauri A is roughly like using a scientific instrument designed to detect individual whispers across a concert hall and turning it towards someone shouting through a megaphone, 6 inches from the microphone. The instrument is extraordinarily good at its job. Its job was not this. The specific instrument used for the Alpha Centauri campaign is called MIRI, the mid-infrared instrument. MIRI observes at wavelengths between roughly 5 and 28 micrometers. The mid-infrared range, where objects emitting from their own residual heat rather than from reflected starlight are best detected. A mature gas giant planet, billions of years old, no longer glowing from formation but still warm from the slow contraction of its interior and the absorbed radiation of its host star, would emit most strongly in exactly this wavelength range. MIRI's 15.5 micrometer filter was identified as the optimal channel for the search, the wavelength where the expected planetary signal was strongest relative to the stellar background. MIRI includes a coronagraph called the four-quadrant phase mask. This device works through a principle of destructive interference. Light waves from the star are manipulated by a specially engineered mask that splits the incoming wavefront into quadrants and introduces precise phase shifts between them. When these shifted wavefronts recombine, they cancel each other out through destructive interference. The star's light is suppressed by factors of hundreds to thousands. Light arriving from slightly different angles, such as from a planet a few arcseconds away, does not experience the same cancellation and passes through with much less suppression. The coronagraph creates an artificial eclipse, a tiny region of darkness around the star's position where faint companions can emerge. For typical coronagraphic targets, bright stars at distances where planetary companions can be resolved comfortably outside the coronagraph's inner working angle, this system works excellently. Hundreds of successful high-contrast campaigns have been conducted. Alpha Centauri violated every assumption the coronagraph's standard procedures rested on. The target was too bright for standard acquisition. Normal target acquisition involves pointing the telescope at the star, centering it on the detector, and fine-tuning the pointing using the star's own light for guidance. For Alpha Centauri A, this procedure would have saturated JWST's fine guidance sensors and risked damaging the detectors. The star's brightness exceeded the safe input range by a substantial margin. The star's rapid proper motion meant that its position shifted measurably between observation epochs, requiring fresh calculations of its exact coordinates for every session. The binary companion guaranteed that even perfect suppression of Alpha Centauri A would leave massive scattered light from Alpha Centauri B, polluting the field. The team's solution to the brightness problem was a technique called blind offsetting, and it had never been executed at this level of precision in JWST operations. The idea, instead of pointing at Alpha Centauri A directly, the telescope would first lock onto a nearby reference star of manageable brightness. The team selected Epsilon Muscae, a red giant star about 330 light-years away in the constellation Musca, bright enough for safe acquisition, but dim enough to avoid saturation. From Epsilon Muscae's precisely known position, the telescope would execute a calculated angular offset that would, if the math was right, place Alpha Centauri A behind the coronagraph mask without the telescope ever looking directly at it. The math required knowing both stars' positions to accuracies measured in milliarc seconds. Alpha Centauri's own position is complicated by parallax, its apparent shift against the background of distant stars as Earth moves around the Sun. At 4.37 light-years, Alpha Centauri's parallax is enormous by stellar standards, 750 milliarc seconds. This means its apparent position on the sky shifts by 750 milliarc seconds over the course of a year as Earth's perspective changes. Coordinates calculated for January are wrong in March. The team built software that automatically computed updated offset values, incorporating the exact date and time of each observation. The first attempts in 2023 failed. The blind offset maneuver worked imperfectly. Coronagraph performance was degraded. The binary companion's light caused worse contamination than models predicted. The data was unusable. Failure is the price of attempting the impossible. The team analyzed what went wrong and developed a modified strategy. They improved the pointing procedure, refined data reduction techniques for handling the binary's contamination, and ran exhaustive simulations before attempting again. In mid-2024, they tried again. The modifications worked. For the first time in history, JWST could observe Alpha Centauri A with sensitivity approaching theoretical limits. The team received approval for a full campaign. In August 2024, 3 long observation sequences were executed. Each lasted hours. The coronagraph blocked Alpha Centauri A, while MIRI's detector collected whatever faint infrared signals existed in the surrounding space. The raw data that came back looked like nothing. This is important to understand because it's where the gap between scientific imaging and human intuition becomes most acute. A coronographic image of a bright nearby binary star system is not a picture, it is a chaos of overlapping patterns. The masked star creates diffraction ripples extending outward from the mask edges. Alpha Centauri B, unmasked and blazing nearby, casts scattered light across the entire field. Detector noise creates random fluctuations throughout. Everything that is not a planet looks like a planet, and everything that is a planet looks like everything else. Extracting signal from this requires a technique called reference star differential imaging. The team observed other stars using identical coronographic configurations, stars that have no planetary companions. These reference observations show how the coronagraph and telescope behave when there is nothing there. Subtracting the reference pattern from the Alpha Centauri data removes the systematic optical artifacts while preserving any signal that appears only around the target star. Then come mathematical cleaning algorithms, principal component analysis, and Kahunen-Loew image processing. These techniques identify and remove correlated patterns in the data that reference subtraction alone cannot catch. Each algorithm strips away another layer of contamination. Applied in sequence, they peel the data like an onion, removing layer after layer of noise, until whatever is genuinely present can be seen. What was present was designated S1, at a separation of approximately 1.5 arcseconds from Alpha Centauri A's masked position. A faint point source appeared. At the distance of the Alpha Centauri system, 1.5 arcseconds corresponds to roughly 2 astronomical units, the equivalent of the asteroid belt region in our solar system, within the star's habitable zone. The object's infrared brightness at 15.5 micrometers implied an effective temperature of approximately 225 Kelvin, about -48 degrees Celsius. This frigid temperature is consistent with a mature planet absorbing and re-emitting stellar radiation at this orbital distance. The brightness and temperature together implied a mass in the range of Saturn, approximately 90 to 150 Earth masses. This is the mass range of a gas giant, not a rocky world. Saturn itself contains 95 Earth masses. What the team appeared to have found was not an Earth, but a Saturn, enormous by human standards, but modest by planetary standards. The statistical significance was 5.5 sigma. In the language of science, sigma measures how many standard deviations a signal sits above the background noise. At 5.5 sigma, the probability that random fluctuations produce the signal by chance is less than 1 in 10 million. This threshold exceeds the 5 sigma standard used in particle physics to declare discoveries. It is a number chosen specifically because it is extraordinarily difficult to achieve by accident. The team did not stop at the sigma measurement. They attacked their own results systematically. They searched every astronomical catalogue for known sources. At the detected position, nothing matched. They analyzed whether S1 moved during the August observation. Moving objects are solar system bodies crossing the field during the exposure. S1 was stationary relative to Alpha Centauri A, consistent with gravitational binding. They injected artificial planetary signals into the raw data at known positions and brightnesses, then processed the data blind to verify their pipeline could distinguish real signals from artifacts. S1 behaved like the injected planets, not like the spurious patterns. They split the August data into independent halves and analyzed each separately. Both halves reproduced S1 at consistent positions and brightnesses. Noise rarely agrees with itself. By every measure the team could apply, S1 was real. The Space Telescope Science Institute granted directors discretionary time for urgent follow-up. 2 additional observation campaigns were approved for February and April 2025. If S1 was a genuine planet, it should appear at different positions in each epoch, having moved along its orbit between observations. February observations were executed. The processing pipeline churned through the data. The region where S1 had appeared in August showed only empty space. No strong detection, nothing but random fluctuations. April confirmed it. S1 had vanished. A planet that appears with 5.5 sigma significance, then disappears entirely, demands an explanation. The scientific team explored 3 distinct hypotheses, and the way each plays out tells you something important about the nature of planetary detection at this scale. The first hypothesis, S1 was never real. Despite passing every statistical test, it was an extraordinarily unlikely random fluctuation that fooled the pipeline. This is the simplest explanation and the most deflating. 5 sigma events do occur occasionally. 1 in 10 million is not 0. And the history of exoplanet science includes false positives, detections that passed initial screening and were later retracted. But specific features of the S1 detection work against this explanation. The signal reproduced across independent data subsets, which genuine noise fluctuations rarely do. The injection recovery tests showed the pipeline was not prone to creating false positives of this type. And 5 sigma significance is not a threshold scientists set because they thought anything above it was definitely real. They set it because events above that threshold almost never arise from pure noise. Accepting the noise hypothesis requires accepting that an extraordinarily rare event happened at exactly the most scientifically interesting target in the sky. At the first epoch of the first instrument ever capable of making this observation. That combination of coincidences is possible. It is not comfortable. The second hypothesis, S1 was a background source. A compact, distant galaxy or faint background star happened to lie at the detected position, masquerading as a planet during the August observation. The team's catalog cross-referencing addressed this directly. No known source appeared at the S1 position in any existing dataset. They examined archival images from multiple instruments. They analyzed the spectral color of S1's emission, which was consistent with a thermally emitting planet rather than a distant galaxy. The color of a galaxy differs from the color of a cool planetary atmosphere in ways that mid-infrared photometry can distinguish. The background hypothesis also struggles to explain why the source vanished. If it was a compact galaxy, it would still be there in February and April. Galaxies do not move on month timescales. If it was a background star with high proper motion, that motion would have been detectable within the August data itself, as the position shifted during the long exposure. The third hypothesis, S1, is a genuine planet that moved beyond the reach of the coronagraph's sensitive region between observation epochs. This hypothesis requires the most explanation, because it's the one most people haven't fully thought through, and it's the one that changes the entire interpretation of the non-detections. Coronagraphs do not provide uniform detection capability across the field of view. This is physics, not a design flaw, and it matters enormously. The four-quadrant phase mask suppresses starlight by creating destructive interference in the region closest to the mask center. But light diffraction around the mask's edges creates residual brightness patterns extending outward from the star. These patterns are not uniform. They vary with angle and distance from the star in complex ways determined by the geometry of the mask and the telescope's optical train. At certain distances from the star, the residual diffracted light overwhelms any planetary signal. At other distances, it falls low enough that the planetary signal can emerge. And, crucially, at certain position angles around the star, the mask geometry creates regions of significantly higher contamination than at other angles. The four-quadrant phase mask has boundaries between its quadrants that run in specific directions on the detector. Near these boundaries, the suppression degrades. What this means in practice is that a planet at a given distance from its star might be detectable when it lies at certain position angles around the star, then become undetectable months later when orbital motion has carried it to a different angle, where the coronagraph performs less well. A planet orbiting at 2 astronomical units from Alpha Centauri A, with an orbital period of roughly 2 to 3 years, would move significantly between August 2024 and February 2025. Depending on the orbital eccentricity and inclination, it might have shifted from a favorable position angle to an unfavorable one in exactly that time. The team tested this systematically. They generated millions of simulated orbital configurations consistent with the S1 detection in August 2024. The 2019 VLT ground-based signal at approximately 1.1 astronomical units, and the gravitational stability constraints imposed by Alpha Centauri B's presence. For each simulated orbit, they computed where the planet would be during the February and April 2025 observations, and whether those positions fell within or outside JWST's detection-capable zone. The result: 52% of the gravitationally stable orbits that fit all the available data naturally predict non-detections in both February and April 2025. Not because the planet disappeared, because it moved to where the telescope cannot currently see it. 52%. More than half of all plausible orbits for a real planet would produce exactly the observational pattern that was seen. Detection in August, non-detection in February, non-detection in April. This transforms the interpretation entirely. The disappearance is not evidence against S1's existence. It is consistent with S1's existence under a large fraction of the allowed orbital families. The non-detections provide no positive evidence against the planet. They simply constrain the parameter space, eliminating orbits that would require the planet to be visible during those epochs. Now, let's go somewhere the other discussions of this story haven't fully explored. There are angles to this detection that have been underexplored, and that, when you understand them, make the Alpha Centauri situation feel stranger and more significant than the headline numbers suggest. The first is the exodiacal dust measurement. When JWST observed Alpha Centauri A during the August 2024 campaign, it was not only looking for a planet. The coronagraphic data simultaneously constrained the amount of dust surrounding the star in its inner system. This dust, called exozodiacal dust by analogy with the zodiacal light visible from Earth, consists of tiny particles generated by collisions between asteroids and the evaporation of comets. In our solar system, this dust forms a diffuse cloud in the inner solar system that scatters sunlight into the faint zodiacal glow visible on dark nights along the ecliptic. If Alpha Centauri A hosted a dense debris disk, a thick ring of dust glowing in the infrared, that emission would compete with planetary signals and potentially create false detections or hide real ones. Dense exozodiacal emission is one of the challenges anticipated for future missions designed to directly image Earth-like planets around nearby stars. A star with 10 or 20 times the solar zodiacal dust level poses serious obstacles for planetary detection. The August 2024 JWST data constrained Alpha Centauri A's exozodiacal dust to approximately 5 to 8 times the solar level. This is the most sensitive constraint on exozodiacal dust ever achieved for any star other than the Sun. Previous observations of other stars could only constrain debris disks to levels tens or hundreds of times the solar value. The Alpha Centauri data pushed an order of magnitude deeper. What this means scientifically is that Alpha Centauri A is relatively clean. Its inner system lacks the dense debris that would make planet detection even harder, or that would indicate ongoing violent collisional activity threatening any biosphere. This is quiet news buried beneath the headline of the vanishing planet, but it matters substantially for understanding the system's habitability prospects. A system with low dust levels is a dynamically settled system, one that has burned through most of its early collisional evolution and arrived at something like stability. The second underexplored angle is the orbital inclination problem, and this one is genuinely puzzling. Alpha Centauri A and B orbit each other in a plane that is inclined approximately 79 degrees from our line of sight. Planets forming in a protoplanetary disk around Alpha Centauri A should, under standard formation theory, inherit the disk's angular momentum orientation. The disk's orientation should be determined by the system's total angular momentum, which is dominated by the binary orbital motion. In a binary system, the disk around each star tends to align with the binary orbital plane. Planets forming from that disk should therefore orbit in approximately the same plane as the binary. The surviving orbital solutions for S1 suggest an inclination of roughly 50 degrees relative to the binary orbital plane. That's a difference of 30 degrees between where theory says a planet should orbit and where this one appears to orbit. This is not a small discrepancy. 30 degrees of orbital misalignment requires explanation. Several mechanisms could produce it. The most straightforward is gravitational perturbation from other planets that no longer exist. If the Alpha Centauri A system once had additional planets, and those planets were subsequently ejected through gravitational interactions, their gravitational torques during the ejection process could have tilted S1's orbit to its current inclination. Planet-planet scattering events during the early chaotic phase of planetary system evolution are now understood to be common. Our own solar system shows evidence of past dynamical rearrangement. Jupiter and Saturn likely shifted positions during the first 100 million years of the solar system's history, scattering smaller bodies and reshaping orbital configurations. A second mechanism is Kozai-Lidov oscillations. And this is where the physics becomes both beautiful and deeply unsettling for any potential life in the Alpha Centauri system. Kozai-Lidov oscillations occur when a body orbiting at one inclination is subject to the long-range gravitational influence of a distant third body. The distant perturber, in this case Alpha Centauri b, periodically exchanges angular momentum with the inner planet through a resonance effect. This exchange causes the planet's orbital inclination and eccentricity to oscillate in a specific pattern. As inclination increases, eccentricity decreases, and vice versa. The two quantities oscillate out of phase with each other over timescales ranging from thousands to millions of years. The critical implication: if S1 is currently at 50 degrees inclination with an eccentricity of roughly 0.4, those numbers are not permanent. They are a snapshot of an ongoing oscillation. At different points in the Kozai-Lidov cycle, S1's inclination might be higher and its eccentricity lower, or vice versa. The orbit is not stable in the sense of remaining the same. It is stable in the sense of remaining gravitationally bound, but its shape and orientation are continuously evolving under Alpha Centauri b's influence. What this does to any moon system around S1 is important. Moons orbiting a gas giant that is undergoing Kozai-Lidov oscillations in its own orbit experience a doubly complex gravitational environment. The gas giant's changing orbital shape periodically alters the tidal stresses on its moons. Moons in marginally stable orbits might be destabilized during high eccentricity phases of the Kozai-Lidov cycle. The tidal heating experienced by moons changes as the planet's distance from its star varies through its eccentric orbit. This is not immediately catastrophic for potential habitability. It is a complicating factor of a specific and interesting type that no other known exoplanet situation has presented in quite this way. The third underexplored angle concerns what the eccentricity number actually means for any moon that might orbit S1. The surviving orbital solutions suggest S1 follows a significantly eccentric orbit, with eccentricity values around 0.4. At perihelion, the closest approach to Alpha Centauri A, the planet sits at approximately 1 astronomical unit, roughly Earth's distance from the Sun. At aphelion, its farthest point, it retreats to approximately 2 astronomical units, roughly Mars's distance from the Sun. A planet sweeping between these two orbital distances, in a period of 2 to 3 years, experiences seasonal stellar flux variation of roughly 4 to 1. When it is at 1 astronomical unit, it receives about as much stellar radiation as Earth does from the Sun. When it retreats to 2 astronomical units, it receives about a quarter as much. This is not like Earth's gentle 12% variation between perihelion and aphelion, driven by our nearly circular orbit. This is a fourfold variation, driven by an orbit that swings between orbital distances spanning the entire inner habitable zone range. Now consider a moon orbiting this planet. The moon experiences 2 distinct sources of thermal variation: the varying distance from Alpha Centauri A as the planet swings around its orbit, and the tidal heating generated by gravitational flexing as it orbits the gas giant. Both vary on different timescales. The stellar variation occurs on the 2 to 3 year planetary period. The tidal heating varies on the much shorter orbital period of the moon around the gas giant, probably days to weeks. The combination creates a thermal environment unlike anything in our solar system. Earth's moon experiences almost no tidal heating, because the moon has long since tidally locked to Earth, and the residual flexing is minimal. Saturn's inner moons experience substantial tidal heating, driven by orbital resonances with other moons. But none of our solar system's moons faces a four-fold variation in received stellar flux on multi-year timescales, overlaid on shorter tidal cycles. Whether this environment is more or less conducive to life than a stable environment is genuinely unknown. Complex chemistry is possible under variable conditions. Earth's own climate history, including ice ages and warm periods driven by orbital variations, suggests that biological evolution can occur through periods of significant climate change. But a four-fold variation in received stellar energy every 2 to 3 years, indefinitely, is a much more severe form of variation than anything Earth has experienced. The implications for any hypothetical biosphere on a hypothetical moon of S1 are not clearly negative, but they are deeply uncertain. The fourth underexplored angle is what the August 2026 observation window means, and why it is the most consequential astronomical observation currently scheduled. The orbital simulations that identified which 52% of plausible orbits predicted non-detections in early 2025 also identified when those same orbits would predict S1. Returning to a detectable position, the modeling points to a visibility window centered on August 2026. This is not a vague prediction. It arises from the specific geometry of the coronagraph's sensitive regions and the family of orbits that fit all available data. If S1 is a real planet following one of the surviving orbital families, it should be detectable during the August 2026 window. If the telescope observes Alpha Centauri A during that window and finds nothing, with the same or better sensitivity as the August 2024 campaign, the orbital parameter space that can accommodate a real planet would shrink substantially. It would not shrink to zero. Orbits exist that would keep S1 hidden longer, but they become increasingly contrived, fitting all the data only by requiring orbits with specific properties that become harder to justify. More importantly, if August 2026 produces a detection at a position consistent with orbital motion from the August 2024 position, the case for S1 as a genuine planet becomes overwhelming. Two detections separated by 2 years with positions consistent with Keplerian orbital motion cannot be explained by background contamination, because background objects don't orbit Alpha Centauri A. They cannot be explained by statistical noise, because noise doesn't reproduce at the same position 2 years apart. A third detection, after the 2019 VLT signal, the 2024 JWST detection, and now 2026, would constitute confirmation by any reasonable scientific standard. The universe already knows whether that detection will occur. The planet is either there or it isn't. Its orbit either brings it back into the detectable zone in August 2026, or it doesn't. We are simply waiting for the light to arrive. What makes this situation psychologically interesting and worth sitting with tonight is its fundamental structure. We are not waiting for an experiment whose outcome we can partially influence. We are not building better instruments or developing new techniques that will determine the result. We are simply waiting for a position in an orbit, governed by gravitational physics that has been operating for billions of years without our knowledge, to align with the sensitivity window of a telescope we positioned in space. The answer is not coming. It has already happened. The photons that will either confirm or deny S1's existence at its predicted position in August 2026 have either left that planet or have not. If the planet is there, those photons departed its surface, traveled 4 1/3 light years, and arrived at JWST's detectors, or they will arrive in August 2026. The sequence is determined. We are waiting not for an event, but for our ability to observe an event that the universe has already resolved. This is not unique to Alpha Centauri. All astronomical observation has this quality. We are always looking at the past. But the scale of the past matters. When we look at Alpha Centauri, we are looking 4.37 years into the past. When JWST observes in August 2026, the photons it catches will have left Alpha Centauri in early 2022. The state of the Alpha Centauri system in early 2022 is what we will be measuring. Whether a planet was in a detectable position in Alpha Centauri A's orbit in early 2022 is a fact, fixed and determined, that we simply haven't learned yet. There is a question underneath all of this that the scientific papers don't ask directly, but that follows inevitably from everything we've examined tonight. If S1 is real, and if it hosts moons in the way that Saturn hosts moons, what is the probability that one of those moons has liquid water? The honest answer is, we don't know. The honest follow-up is, the conditions are more interesting than for most of the galaxy's other hypothetical worlds. Alpha Centauri A is nearly identical to the Sun. Its spectrum, the distribution of its light across wavelengths, is similar enough to our Sun's that the same photochemical reactions that drive surface chemistry on Earth would operate in principle on an orbiting body. The star's luminosity is higher than the Sun's, which pushes the habitable zone outward slightly, but S1's orbit sits within that zone for significant portions of its eccentric path. A moon orbiting S1 at a distance that keeps it bound, but avoids tidal lock, would experience sun-like radiation during the periods when S1 is near its perihelion approach. It would receive reduced, but not negligible radiation during aphelion. A thick enough atmosphere on such a moon might buffer the thermal swings, converting what would otherwise be extreme seasonal temperature variations into something more gradual. Titan, in our own solar system, has an atmospheric pressure 1.5 times Earth's, and a surface temperature determined primarily by atmospheric chemistry, not direct solar flux. A moon with a substantial atmosphere around S1 would similarly buffer the variable stellar input. The tidal heating from S1's gravity would provide an additional energy source independent of stellar distance. Enceladus, in our solar system, has a global subsurface ocean not because it's in the habitable zone, it is not, but because tidal flexing from Saturn's gravity provides enough heat to maintain liquid water at depth. A moon of S1 would experience tidal heating that varies with the planet's orbital eccentricity. During high eccentricity phases of the Kozai-Lidov cycle, that heating might increase substantially. None of this constitutes evidence for life. It constitutes conditions that are not obviously incompatible with life's chemistry, and that is a rarer thing than it might appear. In the entire observable universe, the only planetary environment where we have confirmed that life-supporting conditions exist is Earth. Adding even tentative planetary candidates in environments not obviously hostile to chemistry is meaningful, however small the individual probability might be. The nearest Sun-like star to Earth might have a gas giant in its habitable zone. That gas giant, if it exists, might have moons. Those moons, if they exist, might have liquid water. Life, if it arose, would be the nearest extraterrestrial life we have ever found by a factor of thousands, compared to any other candidate. Or the planet doesn't exist, or it exists but has no moons, or the moons exist but are too cold or too hot, or lack the chemistry. Each layer of conditionality multiplies the uncertainty. But the point is not to claim likelihood. The point is to understand what the question actually is. The question is not, is there life at Alpha Centauri? The question is, does a planet exist around our nearest sun-like neighbor that even opens the possibility of asking that question? And the answer to that question, as of tonight, is we are 4 months away from the observation that might tell us. Let's start with a number that has haunted astronomy since 1961. In that year, a young radio astronomer named Frank Drake gathered a small group of scientists at the Green Bank Observatory in West Virginia for a meeting that would become one of the most discussed thought experiments in the history of science. Drake wanted to organize the question of whether intelligent life existed elsewhere in the galaxy into something tractable. He proposed a formula now called the Drake equation, though Drake himself always described it less as a predictive equation and more as a way of structuring ignorance. The equation estimates the number of technologically active civilizations in the Milky Way by multiplying together a series of factors: the rate at which new stars form, the fraction of stars that have planets, the average number of planets per star that could support life, the fraction of those planets where life actually arises, the fraction of those where intelligent life develops, the fraction of those where the civilization develops technology detectable from space, and the length of time such civilizations survive in a detectable state. For decades after 1961, the second factor in the equation, the fraction of stars that have planets, was essentially unconstrained. We had one example: our own solar system. Some astronomers thought planetary formation might be common. Others argued it might be rare, that the particular geometry of our solar system might require unlikely conditions. There was no data. The debate was philosophical. Then came the exoplanet revolution, beginning in the 1990s and accelerating dramatically through the 2000s and 2010s. The Kepler Space Telescope and subsequent missions revealed that planets are not rare exceptions. They are essentially universal. Almost every star has planets. Statistical extrapolation from Kepler's survey suggests that the average star in the Milky Way hosts more than one planet. The second Drake factor, which could have been anywhere from nearly 0 to nearly 1, turned out to be extremely close to 1. This was transformative. It converted billions of stars in the galaxy from possible planetary hosts into probable planetary hosts. It turned the abstract question of whether other solar systems exist into the concrete question of what kinds of solar systems exist and how many have conditions suitable for life. But there is a specific gap in this picture that the Alpha Centauri situation directly addresses, and it is a gap that matters enormously for interpreting the Drake equation. Almost all of the thousands of exoplanets found through the transit and radial velocity methods are statistical detections. We know they exist. We can measure their orbital periods, their sizes, in some cases their masses. We can even analyze the chemistry of some of their atmospheres through transmission spectroscopy, where the star's light passes through the planetary atmosphere during transit and carries the absorption signatures of atmospheric molecules to our instruments. But we cannot study these planets in the kind of detail that answers the questions that actually matter for the Drake equation. We cannot measure whether they have surface liquid water. We cannot determine their geological activity. We cannot assess whether their atmospheric chemistry shows signs of biological activity. The planets found by transit and radial velocity surveys are statistical, not characterizable. Direct imaging is different. When you directly detect a planet's own light, you are receiving photons that have interacted with that planet's atmosphere, that carry information about its temperature, its composition, its cloud structure. You can analyze those photons spectrally and extract chemical information that no other method can provide. Direct imaging is the path to planetary characterization. And direct imaging has a fundamental limitation that has shaped everything about what we know. It works best on young, hot, massive planets orbiting far from their stars. Young planets still glow brightly from the heat of their formation, making them far easier to detect than old, cool worlds. Planets far from their stars are easier to separate from the stellar glare. Massive planets emit more radiation and are larger targets. The result is that every directly imaged exoplanet found before the Alpha Centauri campaign orbits a young star less than a few 100 million years old, at distances typically beyond 10 astronomical units, and has masses ranging from a few Jupiter masses upward. These are not solar system-like planets. They are planetary system infants in the most distant orbits, caught while they still glow with formation energy that will fade over the next billion years. We have never directly imaged a mature planet, a planet billions of years old that has cooled to the temperatures appropriate for its age, orbiting at the distances where habitable conditions are possible, around a star like the Sun. S1, if confirmed, would be the first. This is not merely a record. It is a qualitative shift in what exoplanet science can do. Every directly imaged planet currently known tells us about planetary youth and planetary exteriors. A confirmed S1 would tell us about planetary maturity, about what a gas giant looks like after billions of years of evolution under sun-like radiation, about the atmospheric chemistry of a planet that has had time to develop the complex molecules that form in old, settled atmospheres. For the Drake equation, this matters because the factors involving the emergence of life refer to old planetary systems. Life on Earth took roughly 4 billion years to evolve from simple chemistry to technological civilization. The planets relevant to the Drake equation are not young, hot giants in early formation. They are mature, settled worlds that have had billions of years to develop complexity. We have never characterized a planet from this population through direct imaging. Alpha Centauri A offers the first realistic opportunity to change that. Because it is the only mature, sun-like star close enough to Earth that direct imaging of its planetary companions is achievable with current technology. Now let's talk about the Drake equation factor that is most constrained by the Alpha Centauri situation. The fraction of stars in binary systems that host planets in habitable zones. Approximately half of all sun-like stars in the Milky Way exist in binary or multiple star systems. This has been known for decades. But the gravitational complexity of binary systems was long thought to suppress or prevent planetary formation, particularly for tight binaries like Alpha Centauri AB, where the companion stars approach to within 11 astronomical units. The argument was straightforward. Planets form from protoplanetary disks of gas and dust around young stars. In a binary system, the gravitational tidal forces from the companion star truncate the disk, removing material from the outer regions before it can coalesce into planets. The disk around each star, in a tight binary, is limited to roughly a third of the binary's closest approach distance, about 3 to 4 astronomical units in Alpha Centauri's case. Simulations consistently showed that forming planets in this restricted zone was suppressed or impossible. If this theoretical prediction is correct, then roughly half the Sun-like stars in the galaxy are effectively barren of habitable zone planets. Slashed from the pool of potential Drake equation candidates by the binary companion. The number of potentially life-supporting worlds in the galaxy would be roughly halved compared to an estimate that treated all stars equally. If S1 is real, this prediction is wrong. Not just slightly off, but fundamentally incorrect. A planet at 2 astronomical units around Alpha Centauri A, in the habitable zone, gravitationally stable, surviving in exactly the zone where simulations said planets could barely exist, would demonstrate that binary systems are not hostile to habitable zone planet formation. They are merely challenging environments where the planets that form do so under constraints that our simulations may not have accurately modeled. The implications for the Drake equation are significant. If binary systems can host habitable zone planets, the effective pool of candidate stars for the emergence of life essentially doubles. Instead of searching for life among roughly half the Sun-like stars in the galaxy, we would be justified in searching among all of them. Binary systems would need to be reconsidered not as dead ends, but as unexplored territory. This is not a small revision. The Milky Way contains roughly 100 billion stars. If half are in binaries, and if those binaries were previously excluded from life-hosting candidates, we were potentially ignoring 50 billion stellar systems. If S1 exists and belongs to a class of planets that commonly forms in tight binaries, the census of potentially inhabited worlds in the galaxy becomes dramatically larger. 1 planet, 1 conformation, and the mathematics of life in the universe shifts. Let's now talk about what an actual mission to Alpha Centauri would look like, how it has been envisioned, and how confirming S1 changes the engineering calculation from abstract to urgent. The most concrete proposal for an interstellar mission to Alpha Centauri is Breakthrough Starshot, announced in 2016 with backing from the late Stephen Hawking, physicist Freeman Dyson, and investor Yuri Milner, among others. The concept is elegant in its core idea and ferociously difficult in its engineering. The proposal envisions a fleet of gram-scale spacecraft, each essentially a postage stamp-sized silicon chip, carrying a laser communication system, a camera, and the absolute minimum of instrumentation, attached to a gossamer reflective sail roughly 4 meters in diameter. From a powerful ground-based laser array, the sail would be accelerated by light pressure over a few minutes to approximately 20% of the speed of light. At that velocity, the journey to Alpha Centauri would take approximately 21 years. Adding the time for signals to return at light speed, the mission would return data to Earth in roughly 25 to 26 years after launch. The appeal is obvious. A 25-year round-trip timeline for interstellar data is within a human lifetime. Engineers who designed the spacecraft could potentially see the results. Scientists who proposed the science case would still be alive when the data came back. The engineering challenges are immense. The laser array would need to deliver roughly 100 gigawatts of power in a coherent, precisely aimed beam for several minutes, a capability that does not currently exist in any form. The sail material would need to reflect the laser light with extreme efficiency while surviving the acceleration without tearing. The spacecraft would need to survive decades of travel through the interstellar medium, where cosmic ray bombardment would damage unshielded electronics. And slowing down at the destination is not part of the current concept at all. Breakthrough Starshot probes would fly through the Alpha Centauri system at 20% light speed, spending approximately a day in the system at useful range, capturing whatever images and measurements their tiny instruments could gather before receding into the darkness. The science return per probe is therefore limited. At 20% light speed, the probe cannot pause to study anything in detail. It sweeps through the system once, recording what it can, then transmits its data back over the following years before its battery expires. But limited does not mean worthless. A fly-through at close range would produce direct images of any planets in the system, with angular resolution impossible from Earth. It would measure the magnetic fields, particle environments, and infrared emission of any worlds it passed near. If there is a gas giant at 2 astronomical units, a probe passing within a few million miles would see it clearly, would detect atmospheric emission, would potentially observe any large moons. If there is a rocky planet in the habitable zone that our current instruments cannot detect, a close fly-through might reveal it. Breakthrough Starshot is a mission into uncertainty. You are sending a fleet of expensive, technically demanding spacecraft to a target that might have nothing interesting when you arrive. The science justification rests on possibility. There might be planets worth seeing. The engineering investment is hard to justify on possibility alone. With a confirmed S1, the mission has a specific, known target. Engineering can optimize for that target. Instruments can be designed around what needs to be measured, given what is already known about the planet's temperature, size, and orbit. Mission trajectory can be calculated to fly through the habitable zone at the right time in S1's orbit, maximizing the probability of capturing it near aphelion where it spends more time, and where its detection was first achieved. The difference between a mission to somewhere and a mission to a known destination with characterized targets is the difference between geological exploration and mining. Confirmation also changes the timeline pressure. The current Breakthrough Starshot concept is a project for decades from now, pending the development of laser array technology that doesn't yet exist. But confirmation of S1 would immediately elevate Alpha Centauri from one of several possible interstellar targets to the target. Resources, attention, and engineering effort would concentrate. A confirmed planet is the argument that makes the mission feel necessary rather than optional. And there is a subtler point underneath all of this. The miniaturized spacecraft concept of Breakthrough Starshot envisions probes that are essentially disposable, single-use instruments that fly through and never return. This is fine if you are establishing that something exists. If you want to study it further, if you want to know about atmospheric chemistry in detail, if you want to search for biosignatures, if you want to understand the moon system, you need something that can slow down and remain in orbit. Slowing down at 20% of the speed of light requires either carrying propellant for deceleration, which for current technology would mean the spacecraft would need to be almost entirely propellant by mass, with almost no room for instruments, or finding another way. Proposals have been made for using the Alpha Centauri system's own stellar wind as a brake, for using laser sails in reverse, for staging the deceleration across multiple phases. None of these are solved engineering problems. They are concepts at the level of theoretical plausibility. The point is not that these problems are unsolvable. The point is that they become worth solving once you know there is something worth visiting. S1's confirmation is the event that transforms interstellar deceleration from an interesting physics problem into an urgent engineering challenge. Now let's talk about the next generation of instruments, because the story of Alpha Centauri does not end with James Webb. 3 ground-based observatories currently under construction will collectively transform what is possible for nearby star systems within a decade of this writing. The extremely large telescope, being built by the European Southern Observatory on Cerro Armazones in Chile's Atacama Desert, will have a primary mirror 39 meters in diameter when it achieves first light, currently anticipated before 2030. To understand the scale, the largest optical telescopes currently in operation have primary mirrors roughly 8 to 10 meters across. The ELT's mirror will have a light-collecting area roughly 16 times larger than current large telescopes. This is not a modest improvement. It is a step change. The ELT's coronagraphic instruments, specifically a system called METIS, the mid-infrared ELT imager and spectrograph, is designed with Alpha Centauri explicitly in mind. METIS incorporates a coronagraph and will achieve angular resolution and contrast ratios that exceed what JWST achieved with MIRI. The larger aperture provides fundamentally better angular resolution. The ground-based location, when combined with the ELT's adaptive optics system, HARMONI, allows correction of atmospheric distortion in real time to a degree that approaches the diffraction limit of the mirror. There is an important trade-off to acknowledge. Space telescopes operate above the atmosphere entirely. JWST's thermal stability and its absence of atmospheric seeing provide advantages for certain types of observation, but the ELT's sheer size overcomes these advantages in many regimes. A 39-meter mirror collects more photons per second than any space telescope ever launched. For observations where sensitivity is the limiting factor, more area wins. For Alpha Centauri, the ELT changes two specific things. First, sensitivity. The LT will be able to push the detection threshold to smaller, cooler planets than JWST can reach. A Neptune-mass planet at Alpha Centauri A, something too faint for JWST's MIRI at 15.5 micrometers to detect with statistical significance, might be detectable with the ELT's larger aperture and optimized coronagraph. A rocky planet in the habitable zone remains beyond direct imaging capability, even for the ELT. But the planet population that is accessible expands substantially. Second, continuity. JWST observes in blocks of scheduled time, typically measured in hours to days, separated by weeks or months when the telescope is doing other science. Ground-based telescopes can observe the same target every clear night for months on end. For tracking the orbital motion of a planet like S1, frequent observations over an extended baseline are enormously valuable. Each observation adds a data point that constrains the orbital parameters. A dense time series of position measurements over a year or two would pin down S1's orbit far more precisely than the sparse JWST campaign observations can. This would resolve the eccentricity uncertainty, would determine the inclination more precisely, would allow prediction of visibility windows years in advance, rather than the broad probabilistic windows the current models provide. The 30-meter telescope, planned for Mauna Kea in Hawaii, offers similar capabilities. Its primary mirror is 30 meters in diameter, smaller than the ELT, but still roughly 10 times the collecting area of current large telescopes. The TMT has been the subject of significant controversy regarding the cultural significance of its planned site on Mauna Kea, and as of this writing, its construction timeline remains uncertain. But if it is built, it will extend the Northern Hemisphere's ability to study Alpha Centauri, which is primarily a Southern Hemisphere target, but is observable from mid-latitudes, with some seasonal limitation. The giant Magellan Telescope, under construction at the Las Campanas Observatory in Chile, combines 7 8.4-meter mirrors in a configuration that achieves an effective aperture of 24.5 meters. The GMT is further along in construction than the ELT and may achieve early science operations sooner. Its coronagraphic instrument is designed for direct imaging of planetary companions around nearby stars. Alpha Centauri is one of its primary science targets. The combination of JWST observations and one or more of these extremely large telescopes creates something powerful. A multi-instrument, multi-epoch, multi-wavelength characterization campaign for the Alpha Centauri system that no single telescope could conduct alone. JWST provides space-based mid-infrared sensitivity above the atmosphere. The LT provides ground-based near-infrared and thermal infrared capability with far greater collecting area. Together, they cover a wider wavelength range with higher sensitivity than either can achieve independently. This matters for characterization because different atmospheric molecules absorb and emit at different wavelengths. Methane has strong absorption features in the near-infrared. Water vapor appears prominently at multiple mid-infrared wavelengths. Carbon dioxide has absorption features in both the near and mid-infrared. Ammonia appears in the mid-infrared. A gas giant's atmospheric composition is like a fingerprint, and different instruments reading different wavelength ranges trace different parts of that fingerprint. A confirmed S1, studied in combination by JWST and the ELT over several years, would provide the first detailed atmospheric characterization of a mature gas giant orbiting a Sun-like star. We would learn whether Alpha Centauri A's slightly higher ultraviolet output changes the photochemistry of its gas giant's upper atmosphere relative to what we see on Jupiter and Saturn. We would learn whether the planet's eccentric orbit produces detectable seasonal variations in its atmospheric emission, as it cycles between its perihelion and aphelion positions. We would begin to understand how planetary atmospheres evolve over billions of years under conditions similar to, but not identical to those in our own solar system. This knowledge is not academic. It is the foundation for the next generation of planetary science questions, the ones that will guide the design of future missions and future telescopes. Every major space telescope in history has been partly justified by the previous telescope's discoveries. Hubble's findings justified Webb. Webb's findings will help justify the Habitable Worlds Observatory, currently in early concept development, which would be designed specifically to directly image Earth-like planets around nearby stars, including Alpha Centauri. The chain of discovery leads directly from S1, if confirmed, to the design specifications of the instrument that might eventually detect a rocky world in Alpha Centauri A's habitable zone. Let me now address something that the reference videos on this topic have not clearly explained. The specific way that detection bias has shaped our understanding of exoplanet populations, and why that bias makes Alpha Centauri's planetary system potentially more representative of the galaxy than our own solar system. When we survey the population of known exoplanets, we see a distribution that is heavily skewed toward large planets in short-period orbits. Hot Jupiters, gas giants orbiting so close to their stars that their years last only a few days, are dramatically overrepresented in exoplanet catalogues relative to their true abundance. Neptune-sized planets at intermediate distances are common in the catalogue. Earth-sized planets in habitable zones are the most difficult to detect, and therefore the most underrepresented, despite theoretical predictions suggesting they should be among the most common planets in the galaxy. This is detection bias. Every survey method finds what it is best at finding. The transit method finds planets whose orbits happen to cross the stellar face as seen from Earth, which favors close-in planets because close-in planets have larger transit probabilities. The radial velocity method finds planets with strong gravitational tugs, which favors massive planets and close orbits. Direct imaging finds bright, young, massive, distant planets. The catalogs look like what the methods are sensitive to, not like what the universe actually contains. A critical consequence. Our census of exoplanet demographics is most reliable for planet types that are easy to detect and least reliable for the planet types most relevant to life. We have excellent statistics on hot Jupiters. We have poor statistics on warm Neptunes. We have extremely poor statistics on rocky habitable zone planets. We are trying to assess the abundance of the most important thing by extrapolating from the thing we can measure most easily. Alpha Centauri A is the only nearby Sun-like star where we can attempt direct imaging of planets in the mature, cool, moderate distance regime that is relevant to the Drake equation's life-supporting parameters. Every other Sun-like star that is close enough for direct imaging attempts is either younger and therefore hosts brighter, easier to detect planets that don't represent the mature population, or is in a simpler, non-binary system that might not represent the full range of planetary architectures, or is distant enough that detection sensitivity is marginal. If we can characterize the planetary system of Alpha Centauri A, we are directly sampling the part of the exoplanet distribution that matters most for understanding life in the galaxy. And we are doing so for a star that represents the most common type of stellar environment in the Milky Way, an old, sun-like star, roughly solar composition, in a binary system. This is why finding a planet at Alpha Centauri is not primarily about that one planet. It is about what that planet represents, statistically. It is about whether the detection bias in our catalogs has caused us to under- or overestimate the abundance of mature, habitable zone planets around the most common stellar environments. If S1 exists, it is a calibration point. It is a way of checking whether our theoretical models of planetary formation in binary systems are correct or need revision. It is a data point in a distribution that currently has essentially no data in the most scientifically important part of its parameter space. Let's talk about what the specific properties of S1 teach us about planetary formation in binary systems, because these details have been underexplored. The survivors of the gravitational stability analysis, the orbital families that fit all available data and remain stable against long-term perturbation by Alpha Centauri B, share several features that collectively paint a specific picture of what kind of planet S1 might be and how it got there. The eccentricity is high for a mature planet in a system this old. Earth's eccentricity is 0.017, barely distinguishable from circular. Jupiter's is 0.049. Saturn's is 0.057. Mars reaches 0.093, the highest of the 8 solar system planets. S1's estimated eccentricity of roughly 0.4 is almost 5 times Mars's and almost 8 times Jupiter's. Among the solar system's major planets, this would be anomalously high. It would not be anomalous among exoplanets in general, where high eccentricities are common and well documented. But those high eccentricities are typically associated with gravitational interactions in the early history of a planetary system that have since stabilized. In a binary system like Alpha Centauri, there is an ongoing source of gravitational perturbation, the companion star itself. Alpha Centauri B, even at its current separation of roughly 20 astronomical units, exerts tidal torques on any planet orbiting Alpha Centauri A. These torques don't immediately disrupt S1's orbit, but over millions to billions of years, they can pump the eccentricity upward through the Kozai-Lidov mechanism discussed in Part 1. This means S1's current eccentricity might not reflect its formation state. It might reflect the cumulative effect of billions of years of gravitational interaction with Alpha Centauri b. A planet that formed in a nearly circular orbit might have had its eccentricity pumped up over geological time by the companion's tidal influence. The implication is interesting. We might be seeing a planet whose orbital architecture has evolved significantly from its formation state, sculpted by the binary companion into its current configuration. This is a form of ongoing geological process, not of rock and erosion, but of gravity and orbital mechanics, that has no parallel in our solar system. Our planet's orbits have changed over time, but they are not currently being actively reshaped by a distant binary companion in real time. If the Kozai-Lidov mechanism is actively pumping S1's eccentricity, then the planet's current state is one phase in an ongoing cycle. At maximum eccentricity, the planet would come closest to Alpha Centauri A at perihelion, experiencing much stronger stellar radiation for a brief period. At minimum eccentricity, when angular momentum has been exchanged back to inclination, the orbit would be more circular and the temperature variation more moderate. The timescale of these cycles depends on the system parameters, the masses of the stars, their separation, the planet's orbital parameters. For Alpha Centauri, Kozai-Lidov timescales are estimated in the range of millions to tens of millions of years. S1 has been orbiting for roughly 5 billion years, meaning it has undergone hundreds of complete Kozai-Lidov cycles since formation. The current state is simply one phase in a cycle that has been running for the entire history of the solar system. For any potential moon system, this has a specific implication. The tidal heating experienced by a moon depends on the eccentricity of the moon's orbit around the gas giant and on the distance between the gas giant and the host star. Both change as the Kozai-Lidov cycle evolves. During periods of high planetary eccentricity, the planet's perihelion approach delivers stronger gravitational tides to any orbiting moons, potentially increasing internal heating. During periods of low eccentricity, the tidal environment is gentler. Over billions of years, this cycling would produce alternating periods of higher and lower geological activity on any moon. If a moon has a subsurface ocean maintained partly by tidal heating, the ocean's depth and temperature would vary across Kozai-Lidov cycles. The surface might freeze and melt repeatedly on timescales of millions of years. This is not an environment identical to Earth's stable relationship with the Sun, but it is not obviously incompatible with biology either. Life on Earth has survived ice ages, warm periods, mass extinctions, and dramatic changes in atmospheric chemistry. The question of whether biology could maintain continuity across million-year cycles of changing tidal heating is genuinely open. What we can say is that S1's system, if it hosts moons, represents a planetary environment where the geological driver of habitability, the heat source, is not fixed but oscillates on geological timescales. Whether that is a feature or a bug from life's perspective, we don't know. It might drive the kind of environmental variability that pushes chemistry toward complexity. It might periodically sterilize the moon. We don't have the tools yet to distinguish these possibilities. Now let's think about the detection itself in the context of scientific methodology. Because the story of S1 illustrates something important about how science actually works at the frontier that gets lost in the simplified version of events. Scientific discovery is often presented as a linear progression: observation, hypothesis, test, conclusion. In reality, particularly at the cutting edge of observational capability, It looks much more like what happened with S1. Detection, skepticism, alternative hypotheses, simulations, constraints, qualified conclusions, and then waiting for new data to further constrain the possibilities. The 5.5 sigma significance of the August 2024 detection is a statement about statistical probability, not about physical reality. What it says is that if S1 were not present and the data contained only noise and systematic artifacts, the probability of seeing a signal this strong by chance is less than 1 in 10 million. That is an extremely low probability. It is not zero. And crucially, it assumes that all sources of systematic error have been correctly characterized. In an observation as technically demanding as the Alpha Centauri campaign, that assumption is something the team worked hard to verify, but cannot be absolute. The history of physics and astronomy contains examples of signals that exceeded 5 sigma and turned out to be artifacts. The claimed detection of gravitational waves from the early universe in 2014 by the BIC EP2 experiment, which exceeded 5 sigma significance, but was later shown to be primarily polarized light from galactic dust. The reported faster-than-light neutrino results from the Opera experiment in 2011, which turned out to be a loose optical fiber connector. Multiple claimed detections of exoplanets that were later retracted when improved analysis showed stellar activity mimicking the planetary signal. In each case, the original team did careful work. The methodological error was subtle. The 5 sigma threshold protected against statistical noise but not against systematic error that was present in the data in a non-random way. This is not an argument against the S1 detection. It is an argument for exactly the approach the team took. State the result clearly, state its statistical significance, that were tested, acknowledge which cannot be fully excluded, and specify what future observations would confirm or deny the detection. This is how science is supposed to work. The August 2026 observation window is important not just because it might confirm the planet. It is important because it represents a pre-specified test. Before the observations occur, the orbital models have made a prediction. S1 should be detectable at approximately a certain angular position from Alpha Centauri A during August 2026. If the planet is detected near that predicted position, the prediction was correct. If not, the models require revision. This pre-specification matters enormously. In statistics, there is a concept called p-hacking, or harking, hypothesizing after results are known, where a researcher examines data, finds a pattern, and then formulates a hypothesis that the pattern was what they were looking for all along. This inflates false positive rates dramatically. The antidote is pre-specification. State what you expect to find before you look. The orbital models for S1 were constructed from data available before August 2026 and make specific predictions about what that observation should show. This makes August 2026's result a genuine test, one that the planet hypothesis can pass or fail. A confirmation at the predicted position would be significantly stronger evidence than any single observation epoch, precisely because it was predicted before the observation occurred. Let me now address the question of what we do not know about Alpha Centauri A's planetary system, and why that ignorance is itself scientifically important. The sensitivity limits of the August 2024 JWST campaign would have detected any Jupiter-mass planet orbiting beyond approximately 2 astronomical units from Alpha Centauri A. The non-detection of any such planet in that region, other than S1, tells us that the outer region of Alpha Centauri A's accessible zone, the region beyond 2 astronomical units up to the dynamical stability boundary at roughly 3 to 4 astronomical units, does not contain an additional giant planet. This is meaningful because multiple giant planets in close proximity tend to dynamically destabilize each other over millions of years. The presence of S1 alone in the outer zone, without a second giant planet nearby, is consistent with S1 being in a long-term stable configuration. If there were a second giant planet on a crossing or resonant orbit, the system's long-term stability would be doubtful. But the inner system remains essentially uncharacterized. Between Alpha Centauri A and approximately 1 astronomical unit from the star, direct imaging is not currently possible. The coronagraph's inner working angle, the minimum angular separation at which it achieves useful contrast, corresponds to roughly 1 astronomical unit at Alpha Centauri's distance, under current operational parameters. Anything orbiting closer than that is hidden in the stellar glare, even with the coronagraph active. This inner zone is where rocky, potentially habitable planets would orbit. Alpha Centauri A's habitable zone runs from roughly 1.2 to 2.5 astronomical units. Given its luminosity, the inner edge of the habitable zone is within the coronagraph's exclusion zone. A rocky planet at 1.3 astronomical units from Alpha Centauri A, equivalent to Venus's orbit in our solar system, but in a wider habitable zone, would be invisible to current JWST observations. Radial velocity surveys have attempted to detect such inner planets through their gravitational tug on the star. The challenge, as discussed in Part 1, is the binary companion's much larger velocity signal that must be precisely modeled and subtracted. Current radial velocity precision at Alpha Centauri A allows detection of planets roughly down to a few Earth masses at close orbital distances. But uncertainties in the binary orbit model limit confidence. The claimed 2012 detection of an Earth mass planet around Alpha Centauri B, later retracted, illustrates exactly how these model dependencies can create false positives. Future improvements in radial velocity technique, particularly high-resolution spectrographs with more precise wavelength calibration, and improved binary orbit models incorporating more observational data, will push the detection threshold lower. The Espresso spectrograph on the Very Large Telescope in Chile has already achieved radial velocity precision approaching 30 centimeters per second, 10 times better than previous instruments. An Earth-mass planet in the habitable zone of Alpha Centauri A would produce a velocity signature of roughly 30 centimeters per second. Espresso is at the edge of detecting it, but the binary model uncertainties remain limiting. The new generation of extremely large telescopes will dramatically improve radial velocity sensitivity through their larger light collecting area, which provides higher signal-to-noise ratios that allow finer wavelength measurements. The ELT's ANS spectrograph, designed for ultra-high resolution spectroscopy, aims for radial velocity precision of a few centimeters per second. This would be sufficient to detect Earth-mass planets in the habitable zone of Alpha Centauri A, provided the binary model is well enough characterized. The picture that is emerging then is one of layered exploration. James Webb opened the outer zone of Alpha Centauri A's accessible system and found S1. The ELT and its companions will probe the outer zone more deeply, with higher sensitivity, and will begin accessing the inner zone through improved radial velocity. The Habitable Worlds Observatory, if funded and built in the 2030s, would bring the inner habitable zone into direct imaging reach for the first time. Each layer reveals what lies behind it. And the Alpha Centauri system, precisely because it is the nearest Sun-like star, is the place where this layered exploration proceeds fastest and reaches deepest. There is a dimension of this story that the scientific papers don't dwell on, but that is worth stating clearly, because it shapes why this question matters in the way that it does. The search for planets around Alpha Centauri A is, at some level, a search for the answer to a question that has been asked implicitly since the first human looked up at the night sky and felt something in the presence of all that distant fire. The question is not primarily astronomical. It is existential. It is the question of whether we are alone. Not alone in the statistical sense, not the abstracted sense of whether biology has arisen somewhere in the galaxy's billions of star systems, but alone in the local sense. Alone in the sense that matters for every concept of what human destiny might include. Are we alone in our cosmic neighborhood? Is there anything anywhere near us that we might one day reach and find? Alpha Centauri is not the galaxy. It is our immediate vicinity. 4 light-years is not a trivial distance. No human technology has ever crossed it, and the fastest technology we currently have would take thousands of years to do so. But it is a distance that is at least conceptually traversable. It is a distance that proposals exist for crossing within a human lifetime, with technology that is at least theoretically coherent. It is the only stellar system other than our own that sits within range of even the most optimistic current proposals for interstellar travel. If there are planets at Alpha Centauri A, if there is a gas giant in the habitable zone with moons, if the chemistry of life has arisen there in any form, that discovery changes the meaning of human existence in a way that is difficult to overstate. It means we are not the only example. It means the universe produces life not as a singular, improbable miracle, but as something that happens, something that can happen within a few light years of any given inhabited world. It means that the universe, as a whole, is alive in a way that we did not know before. If there are no planets at Alpha Centauri A, or if planets exist but show no signs of life, that is also an answer. And it is also important. The absence of detectable life at the nearest star does not prove life is rare, but it constrains the probability distribution. It tells us that whatever process produces life does not guarantee its presence at every available site. It tells us something about the rarity or the conditions required for biology. Either answer to the Alpha Centauri question changes how we understand our place in the universe. Either answer is worth knowing. And we are at the moment in history when knowing is becoming possible. This is not hyperbole. 100 years ago, we did not know whether other stars had planets. 50 years ago, we had no way to detect them even if we suspected they existed. 20 years ago, we had found thousands of planets, but none around the nearest star. Today, we have a candidate planet in the habitable zone of the nearest Sun-like star, supported by a 5.5 sigma detection that has not been convincingly explained away, with a prediction for its reappearance that will be tested within the year. We are standing at a specific moment in a long story that began when the first creature looked at the stars and wondered. The wondering has been accumulating for tens of thousands of years. The tools to turn it into knowledge have been developing for 400 years since Galileo first pointed a telescope at the sky. And now, the tools are sharp enough to see. Let's bring it down to the human scale for a moment, because everything we've talked about tonight risks becoming abstract, and abstraction is the enemy of wonder. You are, at this moment, sitting on the third planet of a star in the Milky Way galaxy. That star has 8 planets and numerous smaller bodies. The third planet developed life approximately 4 billion years ago. That life evolved through countless forms over hundreds of millions of years, until, roughly 300,000 years ago, a species appeared that was different from every other thing that had lived before it. A species that could model the future, that could represent abstract concepts, that could ask questions about things it had never directly experienced. That species invented astronomy. It built telescopes. It launched them into space. It pointed them at the nearest sun-like star and found, perhaps, a world. The nearest sun-like star is 4 light-years away. The light from that star, the light that Alpha Centauri A is emitting right now, will reach Earth in 4 years. The light that has already reached Earth tonight. The light you might see if you step outside on a clear night in the southern hemisphere and look for the bright yellowish star in Centaurus. That light left Alpha Centauri A roughly 4 years ago. It left when there was a planet either present in the detectable zone of its orbit or not present. That fact is already embedded in the light that's reaching you. You are looking at an answer that you cannot yet read. The James Webb Space Telescope is trying to read it. It will try again in August 2026. And whatever the data shows, the question it answers is one of the most important questions our species has ever asked. This is why it matters that we keep looking. Not because finding a planet around the nearest star will immediately change daily life for any person on Earth. Not because the knowledge has direct practical applications, but because we are the species that asks questions. And some questions are worth asking no matter what the answer costs to obtain. The question of whether we are alone in our cosmic neighborhood is one of those questions. The James Webb Space Telescope, the extremely large telescope, the Breakthrough Starshot proposal, the Habitable Worlds Observatory currently in early planning stages. These are not science projects. They are the species' attempt to answer something it has wondered about since consciousness began. They are humanity looking up. Let's talk about what the atmospheric chemistry of S1 might actually look like, because this is a dimension of the story that requires a deeper technical look than it usually gets, and it changes how we think about what JWST could ultimately reveal if the planet is confirmed, and follow-up spectroscopy becomes possible. MIRI's detection of S1 in August 2024 used a single photometric filter centered at 15.5 micrometers. This gave the team a brightness measurement at 1 wavelength, from which they derived an estimated temperature and a rough mass estimate. This is analogous to taking a photograph of a person with a single color of light and then trying to determine their age, health, and occupation from only that image. You can make inferences, but they are limited and uncertain. Spectroscopy is fundamentally different. Instead of measuring brightness at a single wavelength, spectroscopy disperses incoming light into its component wavelengths and measures brightness across a range simultaneously. The resulting spectrum is a detailed fingerprint of the object's physical and chemical state. Different molecules absorb and emit radiation at specific wavelengths, determined by quantum mechanics. Wavelengths that are as distinctive as barcodes. Methane absorbs strongly at wavelengths around 3.3 micrometers and 7.7 micrometers. Water vapor has absorption features throughout the mid-infrared. Carbon dioxide absorbs prominently at 15 micrometers, directly in the range where S1 was detected. Ammonia absorbs near 10.5 micrometers. A spectrum of S1's emission would immediately reveal which of these molecules are present in its upper atmosphere and in what abundances. This is not speculative technology. JWST has already conducted atmospheric spectroscopy on numerous exoplanets, most famously WASP-39b, a hot Jupiter about 700 light-years from Earth, whose spectrum revealed water vapor, carbon dioxide, sulfur dioxide, and complex organic molecules in unprecedented detail. The same technique applies in principle to S1. The scientific questions that S1's spectrum would address are specific and important. First, the carbon-to-oxygen ratio. In giant planet atmospheres, the relative abundances of carbon and oxygen tell you something about where in the protoplanetary disk the planet formed. Material in the inner disk, close to the star, has a different chemical composition than material in the outer disk, beyond the snow line where ice condenses. A planet that formed beyond the snow line and migrated inward carries the chemical signature of cold outer disk material. A planet that formed close to the star never incorporated as much oxygen from ice. By measuring the carbon-to-oxygen ratio in S1's atmosphere, astronomers can determine where in the protoplanetary disk the planet assembled its atmosphere, providing a window into the dynamical history of the Alpha Centauri A system. Second, the methane-to-ammonia balance. These two molecules exist in chemical equilibrium in gas giant atmospheres, but that equilibrium shifts with temperature. At higher temperatures, nitrogen tends to exist as nitrogen gas. At lower temperatures, it combines with hydrogen to form ammonia. Similarly, carbon shifts between carbon monoxide at high temperatures and methane at low temperatures. The balance between these species in S1 spectrum would provide a precise measure of its atmospheric temperature profile, supplementing and refining the temperature estimate derived from simple photometry. Third, the presence or absence of disequilibrium chemistry. In our own solar system's gas giants, observations have revealed molecular abundances that cannot be explained by equilibrium chemistry at the observed temperatures. Phosphine, for instance, is present in Saturn's upper atmosphere at levels far above what equilibrium would predict. This excess phosphine was dredged up from deeper, hotter layers where it is stable, carried upward faster by convection than chemistry could destroy it. The presence of disequilibrium molecules is a tracer of convective mixing, of the vigorous vertical motions that characterize giant planet interiors. S1, with its warmer temperatures driven by Alpha Centauri A's higher luminosity, and its proximity to the star, even at aphelion, might show disequilibrium chemistry patterns different from Jupiter and Saturn. The specific patterns would reveal whether S1's interior convection is more or less vigorous than solar system gas giants, information that constrains its internal structure and energy budget. Fourth, and perhaps most intriguingly, the spectrum would look for any molecular species that is anomalous, any absorption feature that doesn't fit the expected gas giant template. We would be looking for this not because we expect to find biological molecules in a gas giant's atmosphere, but because any unexplained feature demands explanation and might reveal something about the system we don't yet understand. The history of astronomy is full of moments when a spectrum revealed something unexpected that opened a new chapter of understanding. The technical challenge of obtaining S1 spectrum with current technology is real. Photometric detection at 5.5 sigma leaves a margin that's spectroscopic mode, which distributes the same number of photons across many wavelength channels, rather than concentrating them in one, would reduce. The signal-to-noise per wavelength channel would be much lower than for the photometric detection. Getting a useful spectrum might require multiple observation epochs combined, each contributing additional photons that are stacked to build up signal. This is not impossible. It is a matter of allocated telescope time and observational strategy. The August 2026 confirmation campaign, if it succeeds in detecting S1 again, would be followed immediately by proposals for spectroscopic follow-up. The scientific community would treat a confirmed planet at Alpha Centauri A as the highest priority target for spectroscopic characterization available to any instrument on the planet. The telescope time would follow the science. Now let's talk about Alpha Centauri's place in the human imagination. Because this is not merely a scientific question, it is a question that has lived in the human mind for a very long time, in forms that preceded science. And understanding that history clarifies why this particular detection carries emotional weight that other exoplanet discoveries have not. Alpha Centauri has been used for navigation for thousands of years. The indigenous peoples of Australia, whose astronomical traditions are among the oldest in the world, incorporated Alpha Centauri into their sky maps and their stories. The star is named in the navigational traditions of cultures across the Pacific, across southern Africa, across the southern reaches of the Americas. It is one of the pointer stars that indicates the direction of the Southern Cross, which was in turn one of the most reliable directional references for peoples of the Southern Hemisphere. Long before anyone understood what a star was, this particular star was a tool, a guide, something that told you where you were going. When Nicolaus Copernicus and later Giordano Bruno began articulating the idea that stars might be suns, distant and essentially similar to our own, the nearest of those suns became immediately interesting in a new way. If stars are other suns, then the nearest star is the nearest other sun. In 1838, Thomas Henderson made the first successful parallax measurement of Alpha Centauri from the Cape of Good Hope, establishing its distance at roughly 4 light-years. For the first time, a number was attached to the nearest star, 4 light-years, the nearest possible location for another solar system, the closest place that might have planets like Earth. This knowledge entered the culture. By the late 19th century, science fiction had begun exploring the stars as destinations, and Alpha Centauri appeared in stories as the logical first stop on any interstellar journey. H. G. Wells, Jules Verne, and their successors imagined voyages to the stars. Alpha Centauri was always there, the nearest, the most accessible, the most discussed. Throughout the 20th century, as our understanding of planetary formation developed and the first hints of exoplanets began to appear, Alpha Centauri became a focal point for the question of whether life existed elsewhere. Carl Sagan wrote about it. Isaac Asimov wrote about it. Kim Stanley Robinson set his 2312 novel partly in the Alpha Centauri system, imagining a future where its planets had been colonized. Powell Anderson's Tau Zero, widely regarded as one of the finest hard science fiction novels ever written, ends at a new universe, but begins its journey with Alpha Centauri as the first destination. The system has functioned in the human imagination as both the closest point of the possible and the beginning of the infinite. There is something specific about its psychological role that no other star occupies. Alpha Centauri is close enough to feel real, close enough that proposals exist to send probes there in our lifetime with technology that is theoretically coherent. It is not a fantasy destination the way the galactic center is a fantasy destination. Impossibly far, utterly inaccessible. Alpha Centauri occupies the zone between imagination and engineering. You can almost touch it. It sits just at the edge of the possible. This is why the detection of S1 is not just astronomically significant. It is culturally significant. For every human culture that has ever looked at the night sky and wondered what was out there, the nearest answer was always Alpha Centauri. And now, perhaps, we have evidence that the answer is something. A planet. Perhaps a habitable moon. Perhaps, in the most profound sense, the beginning of the answer to whether we are alone. The confirmation of S1 would make Alpha Centauri not just the nearest star, but the nearest planetary system. Not just the nearest planetary system, but one with a habitable zone giant. And that would change Alpha Centauri's role in human consciousness from a symbol of interstellar aspiration to a concrete, specific, characterized place with known properties. Not a direction, but a destination. There is a concept in astronomy called the cosmic perspective, and it is most commonly attributed to Carl Sagan, who spent much of his career trying to explain what astronomy does to your sense of who you are when you truly absorb its implications. The cosmic perspective is not a comfortable thing. It confronts you with scale. The universe is 13.8 billion years old, 93 billion light-years in observable diameter, containing 2 trillion galaxies, each containing hundreds of billions of stars. You are a collection of atoms that has been alive for a few decades on a small planet orbiting an ordinary star in an outer spiral arm of one of those galaxies. The scale comparison is not flattering. But Sagan's point was never that the scale should make you feel insignificant. His point was that the same physics that governs the universe also assembled you. That you are not separate from the cosmos you are examining, but part of it. That the atoms in your body were forged in stellar interiors and scattered by supernovae long before Earth existed. The cosmic perspective, properly absorbed, produces not insignificance but connection. The James Webb Space Telescope and the Alpha Centauri detection offer a specific version of the cosmic perspective that is available at this moment in history and was not available before. Here is what you can now know in a way that was not possible a decade ago. The nearest sun-like star to Earth, the star that your ancestors navigated by, the star that has featured in the dreams of every generation of humans that has ever wondered about other suns. That star may have a planet in its habitable zone. That planet, if it exists, has been orbiting for roughly 5 billion years. For all of those 5 billion years, since before Earth formed, since before life arose on Earth, since before the first animal walked on land, the photons from that planet have been traveling outward in all directions, including toward Earth. Some of those photons reached Earth 4 years after they were emitted, crossing the void of interstellar space, and did not stop. They passed through Earth's atmosphere, struck every surface they encountered, and disappeared as heat. For almost all of human history, those photons arrived, and we had no way of knowing they carried information about a world. And now we do. The James Webb Space Telescope can catch those photons and read their message. You are alive at the moment when the message from the nearest star can first be read. That is not a small thing. That is a moment in the history of a species, a threshold crossing that separates the time before we could know from the time when knowing became possible. Whatever the answer turns out to be, whatever the August 2026 observations reveal, the fact that we are asking the question with instruments capable of answering it is itself remarkable. We have taken the wonder that drove our ancestors to navigate by Alpha Centauri and built it into a machine that can see its planets. There is one more thing worth saying about the structure of this particular mystery, the thing that makes it different from almost every other open scientific question. Most open questions in science are open because the data doesn't exist yet, because the instruments haven't been built, because the experiments haven't been performed. The unknowns are genuinely unknown. They haven't happened yet, or their outcome hasn't been determined. The question of whether S1 will be detected in August 2026 is different. S1 is either in a detectable position in its orbit in August 2026, or it is not. That fact is determined by the gravitational mechanics of the Alpha Centauri system, mechanics that have been running continuously for 5 billion years without our input. The answer exists. It is written in the positions of objects moving through space according to equations that were finalized long before any human being was born. We simply have not received the photons that carry the answer yet. When JWST points at Alpha Centauri A in August 2026, the photons it collects will have left the Alpha Centauri system approximately 4 years earlier, in early 2022. The state of S1's orbit in early 2022 is what will be measured. Where S1 was in early 2022 was determined by its orbital mechanics in 2021 and 2020 and 2019 and all the years before, all the way back to its formation in the protoplanetary disk of the infant Alpha Centauri system 5 billion years ago. The answer to whether S1 exists and where it will appear in August 2026 is not a secret the universe is hiding. It is simply information that travels at the speed of light, and we have to wait for it to arrive. This is always true of astronomical observation. Every telescope observes the past. But normally, the past is so distant that this fact is philosophical rather than immediate. When you observe a galaxy millions of light years away, you are seeing it as it was millions of years ago, before humans existed, before multicellular life existed. The observation and the observed are separated by geological epochs. With Alpha Centauri, the past is 4 years. The light arriving at JWST in August 2026 left its source in early 2022. In early 2022, you were alive. The world you know existed. People you know were living their lives. Alpha Centauri A was also there, its light falling into space in all directions, the state of its planetary system encoded in the photons it emitted. Those photons are traveling toward us right now. Some of them will arrive at JWST in August 2026, and they will tell us something that happened within our own lived memory, at the nearest sun-like star, about whether a planet was there. That is not an abstraction. That is physics, immediate and local and strange. Before we close tonight, let's put the whole thing in perspective. Because it is easy, when you're deep in orbital mechanics and coronagraph sensitivity and statistical significance, to lose the thread of why this matters, in the largest sense. Here is the thread. We have looked at the nearest sun-like star and found something. We don't know for certain what it is. We have a detection that is either a planet in the habitable zone of our nearest stellar neighbor, or a statistical event so rare it would be one of the most improbable coincidences in the history of astronomical observation. Both possibilities are real. The evidence distinguishes between them imperfectly. Future observations will distinguish them better. If it is a planet, it is in the habitable zone. The habitable zone. Not the cold outer darkness where frozen worlds drift, not the scorched inner reaches where oceans boil, but the middle region where the temperature is right for liquid water, the region where, as far as we know, life can exist. If it is a planet in the habitable zone, it might have moons. The gas giants of our own solar system have dozens of moons each. Some of those moons have liquid water oceans. One of them, Enceladus, is actively venting that water into space through geysers. If S1 has moons with similar characteristics, the moons of the nearest Sun-like star's habitable zone planet might have liquid water. If they have liquid water, and if liquid water is the fundamental prerequisite for life that biology suggests it is, then the nearest possible site for extraterrestrial life might not be in a distant galaxy. Might not be thousands of light years away. It might be 4 light years from where you are sitting right now. 4.37 light years. That is not close in any human engineering sense. It is close in a cosmic sense that matters. It is the distance that makes the question answerable. It is the distance that makes the question urgent rather than theoretical. We don't know the answer. We are waiting for the light. And in the quiet before sleep, that waiting is its own kind of wonder. Somewhere out there, encoded in the photons that are traveling toward us right now, the answer is already written. The universe has known for 5 billion years whether S1 exists. We are simply the first creatures in the history of this system who can ask the question and build the instruments to receive the answer. That is extraordinary. That is what we are. Tell us in the comments where you're tuning in from tonight. We read every single one, and knowing where this community is spread across the planet is one of the most grounding parts of doing this work. Drop your city, your country, wherever you are in the world right now. And if this journey through the James Webb detection at Alpha Centauri gave you something to carry into sleep tonight, please like this video and subscribe to Calm Theory for Sleep. It makes a real difference in how many curious people find their way here. The answer to the question of whether our nearest neighbor has worlds is coming. In August 2026, or close to it, we will know more than we know tonight. And when we do, this community will be the first to explore what it means. For now, the light is traveling. The answer is already written. Sleep well.